Okay, let's start. Welcome to tutorial 2. Quick announcement first. The first homework assignment will be published today, perhaps this evening. This tutorial is very relevant for it. I guess it will show some very basic stuff, but it will help you hopefully do the first assignment because various things in the first assignment are very similar to kind of concepts that are in this tutorial. Okay, so let's start. What we're going to see in this tutorial. So first of all, we're going to talk about supervised learning, just generally show the formulation of the problem. I think you should also see the video lecture from the website as specified by the syllabus to see this concept more fully. And we'll show 2 examples of supervised learning in this tutorial. We'll dive into the code. We'll see how to implement them. One example is binary logistic regression, which is a very simple machine learning model. Not deep learning, it's just machine learning for now. But we'll show some concepts that will be relevant later. We'll implement it from scratch just using NumPy. And the second model will be a multi-class version of the first model, which we will implement with PyTorch just to show some extra stuff with PyTorch that will, again, help you during the first homework assignment. Okay. So first thing, just import some libraries. Okay, so let's talk about the problem first, the supervised learning context. So we have a data set with n labeled samples. This is our data that we're working with. I'm marking the superscript I here as the index of a sample. It's not like an exponentiation or anything. It's just an index of a sample. So we have pairs of samples, labeled samples. So we have a vector x, which is a feature vector. It has d features each element, and we have a label, which can be a scalar or a vector. Usually for classification, we have, for example, C classes. So our label will be just a simple number from 0 to C-1. And sometimes we will assume that we get our data set is drawn from some kind of a distribution of pairs of x and y, which is what you'll see in the lecture. This is kind of a probabilistic interpretation, which means that there is no actual deterministic function from x to y, but we're trying to learn some kind of target the p y given x, target the probability distribution. When we say model, what we mean is some kind of parameterized set of functions. For example, and this set is known as a hypothesis class. So for example, this is a hypothesis class of functions of this form. So we have some function phi, and it operates on the affine transform of the feature vector x using some weight vector w and a bias term b. Okay, so if phi is nonlinear, is some nonlinear function, then this hypothesis class is known as the perceptron model. Sorry. So this model has parameters. It has, in this case, the w weight vector and the b bias term are parameters. And it also might have, models sometimes have hyperparameters, which are parameters that are not trained. So you have to choose them in advance. They define your model, but you don't train them. And training basically means, in our context, updating a model's parameters to improve its performance on some given data set. So for example, when we train here, we update the w and the b, but the nonlinear function phi might be a hyperparameter, or some other hyperparameters might exist. You'll see, for example, in deep networks, the architecture of the network is kind of a hyperparameter, and there are others, of course, that are also related to training and stuff like that. Okay, so that was just an example of the problem. Now, when we talk about loss functions, we define a loss function over our current data. So we have a data set D. And our loss function is a measure of how well a specific hypothesis function fits our data. So generally, we call this in-sample loss because it's only on our samples. It's usually some kind of average value of a pointwise loss, L, which is the loss between the hypothesis of the specific sample and its label. So these are pairs, and we transform the sample with H to get a prediction of the Y, of the label. So this term is dependent on our model, and we usually have a regularization term, which is only dependent on the model itself. Sorry, this term is dependent on our data, and this term is dependent only on the model itself. It's a regularization term. For example, we might want our model to be sparse, so we might put a regularization term that penalizes a lot of non-zero weights, or we want our weight to be smaller, things like that. These things depend only on our model parameters, not on the whole data set. Okay, so this is generally a loss. We try to minimize it when we train. What we actually care about is not this loss, is actually the generalization loss, which means the loss over all possible data from that distribution that we assume exists of pairs of X and Y, but we don't have all the data, we just have our sets. So we try to minimize that, and we hope that we'll get a good result in a generalization term. Also, we only optimize over members of our hypothesis class. So we might get an error just because we chose the wrong hypothesis class. Perhaps if we chose a larger hypothesis class or a better hypothesis class, we'd get a smaller loss. So that kind of error is called an approximation error. So it's a different kind of error. So we try to focus on this kind of error. This is the most simple thing we can formulate based on our data set. Okay, so we want to find some kind of parameterization of our model. In the example that I showed W and B, so that we minimize this loss. Okay, so the first and most simple supervised learning context that we can show. We're not going to show an example here, but we'll see it. You'll see it in the homework. Train a simple linear regression model. Is when this model is when the labels are continuous. So in our case, our targets are just real numbers, and we have d-dimensional features, and we're trying to predict some kind of function over these features. The targets could also be d-dimensional, but the thing is they're continuous. They're not class labels. Okay, so in this kind of model, the simplest linear regression model, we just use a linear hypothesis class, which is the same affine transform that I showed you before, but just without the nonlinear function over it. We define our pointwise loss between a given label and the predicted label for a sample. Sorry, we define it as the mean square error, and then we can write our pointwise loss over the whole data set. And in this simple case, we have a closed form solution exists. We don't need to optimize actually anything. If we can invert this matrix of all the data, which might be large if we have a lot of samples, if we can invert it, then we have a closed form solution. Okay. So that's the really most simple model, and we're not going to actually show an example of it. What we're going to see an example of is this model. This is the binary logistic regression model. So it sounds like regression because of the name, but it's actually a classification model. So in this case, it's binary, which means we're classifying our data into two classes. So our target variables are either 0 or 1. So for each sample, we have either a label of 0, which means it's belonging to the first class, or a label of 1, which means it belongs to the second class. Our model in this case will be similar to what we saw before, but the nonlinear function is a specific function called the logistic function, or sigmoid function, which is defined by 1 over 1 plus e to the minus z in this case. And it returns values between 0 and 1, and we will interpret these values as the probability that our specific sample belongs to the class 1. Okay, so that will be our interpretation when we train our model. So we'll get some number, and we'll interpret it as this probability, and we'll try to get this probability to be correct, to be as close to 1 as possible, if that's the correct class. So the loss that we define in this case of the logistic regression is called cross-entropy loss. You can see the term here. So this is the pointwise loss again. It's between a single label and its prediction. It's defined by this expression, which you can think of it very intuitively, because remember that the y's here are just 0 or 1. So either you have this term or you have this term. You never have them together. So it's kind of simple. If y is 1, then you want the y hat to also be 1. Because if it's 1, then you get a 0 loss. Okay? Is that clear? Okay, so that's the cross-entropy loss. Now this loss, to optimize it, there's no closed form solution that we can find in terms of the optimal weights that will bring this loss to a minimum over our data set. But the loss is a convex function, which means we can apply gradient-based approaches. Okay, so basically, if I try to visualize it, what I mean. See if I have some to draw with. So just imagine you have what I mean by convex loss. Imagine if you have just like one parameter, like you just have one w. Okay, so if you have a parameter w and you have a loss, then the fact that it's a convex function of the weights, the loss is a function convex. The loss is a convex function of weights. Means that we can use the gradient information or the derivative of the loss function with respect to the weights to basically find a weight that will bring our loss to some minimum, which is now obviously in complex problems this is not true. Like in deep learning we don't deal with any kind of convex loss targets, but in this simple case it's true. So we know if we'll apply just some kind of gradient-based algorithm, we will find an optimal solution, at least up to some kind of epsilon around the optimum. Okay, so let's look at our functions. Let's just plot them. Okay, so this is just for visualization to see what we're dealing with. Hope you can see that. So this is our logistic function, and this is what the cross-entropy loss looks like. As you can see, for the blue graph, for example, is the case of the true label is 0. So you can see the loss goes to 0 when the predicted label is 0, and vice versa for the other one. So this is what cross-entropy does, and this is what the logistic function does. You can see how it squashes the whole real values, the whole axis of real values into a 0 up to 1. Okay. So let's look at some code and try to implement the model. So again, we're starting with this binary logistic regression model, which is pretty simple. We'll use the library called scikit-learn, which has it has some data sets built in. They're really small data sets. You can they each have a few hundred samples, or maybe some low thousand samples with tens of features mostly. So they're really simple, and you can train them completely in memory. So we're going to show a logistic regression model trained on one of these sample data sets. In this case, we have a data set called the Wisconsin Breast Cancer Database. It has 569 samples. Each sample has 30 features, and there are 2 classes for each sample, of a cancerous tumor, so it's either benign or malignant. So we want to try to use the 30 features of each sample to identify what type of cancer it is. Okay, so let's start to look at some code. Hope it's large enough. If you want, I can try to increase the font size, but hopefully it's better. Okay, so what we're doing here is we're basically just importing the datasets module from sklearn. The module comes with a matrix here of data, which is, you can see the shape of X here. It has 569 rows and 30 columns. So every row is a sample, and the columns are features of the samples. The Y here, the Y vector here are the targets. So we have a target for each sample. Again, the targets will be 0 or 1 because we have 2 classes. And here I am just building the names of the targets. So we have target names. You'll see it in the next. So here the target names are malignant or benign. Okay, and these are the feature names. So you can see we have a bunch of features that were extracted from patient data. I think they were extracted from images of cells, and we're trying to classify them now. Okay, so let's just visualize the data a bit. So we're now using a library called Pandas. We're loading our data into what's called the data frame. It's just something that's useful to show it kind of nicely in this notebook. So you can see this is just to get a feel for the data. You can see we have rows. Each row has a bunch of features and a class label. Okay, that's what we're working with. Okay, so the first thing we want to do is split our data into training and test sets. Again, a very basic thing we do in machine learning. So we will, in this case, again, use something built into sklearn, which is this train test split function. We give it our matrix of our data set and our labels. And we say that we want our test set size to be 30% of our data. And we specify we want to stratify, which means we want to maintain the same ratio of classes in each of the sets. Okay? So that's all we did. So now instead of just x and y, we have x train and y train and x test and y test. Okay, you can see the sizes here. So it just splits our data. You can implement it yourself or use something built in like I did in this case. Next very standard step that you do in most problems is you have to standardize the features, which means there are multiple. You can either squash the dynamic range of each feature to be, for example, in a specific range like 0 to 1 or -1 to 1, or you can standardize by forcing the mean to be 0 and the standard deviation to be 1, like I did in this case here. So basically, what this code does, it calculates the mu, the average of each feature. So that's why the axis here is 0. I'm going over my matrix and calculating the mean of each column. Okay, and same for the standard deviation. And this is important that you have to standardize each feature individually. And another important concept here is that you need to standardize your test set with the same transformation. So I calculated my mu and sigma with the training set, but I'm actually using the same mu and sigma for the test set. Again, the idea is that the test set is unseen data. You're not using it for training. So when you see some kind of sample in the future that you haven't seen before, you don't know how to normalize it unless, except with the same parameters that you use for your training data. So hopefully, if the training data really represents the whole population of the data that exists, this mu and sigma actually means something. If the training data you got does not represent the actual population, then obviously it won't be good to normalize anything else with it. But that's kind of the assumption that we do, because that's the data that we have. Okay, and if you remember from the previous tutorial about broadcasting, what I said, then you can kind of think about what's happening here, where these are actually vectors and the train is a matrix. Okay, so it's actually broadcasting this vector such that it removes the same value from each row in this case. Okay, so that's what we see here. Okay, so now let's implement our model itself. So far we just work with our data, we normalize the features. Let's implement our model. So in sklearn, there's a specific kind of way to implement models. So I'm just gonna use the same API of the class that I implement. There are various advantages to that, which means you can use other features of sklearn with your custom model. And again, you'll do that in the first homework and experiment with very similar thing yourself. Okay, so now I will show you the model. Okay, so let's go over it. So this is my model of binary logistic regression. I have 3 functions here. It's just, I think, 30-something lines of code. So let's start. This model uses an iterative approach based on the gradient, like I explained, and it will basically just run for a given number of iterations and try to update the parameters this number of times until it reaches the best, at least some kind of weight value here. Hopefully low enough. So it's not a very smart model. It's just running for a fixed number of iterations, and we hope it will reach a good enough value. Okay, so let's kind of go over the code just to understand the implementation. So first of all, we're initializing here in the fit function. Fit is the function that uses the training data to calculate the weights of the model. Okay. So here we don't have a weight and bias because we're gonna do a bias trick, which I'll explain in a second. So these are our model parameters. Okay, we're just creating a random vector with d plus 1. D is the number of features plus 1 for the bias. And we're going over our data set n iterations. Each time we're creating a version of our data with a bias feature, which is just basically doing this. I mean, if you take your data, okay, so this is your matrix. You have n by d, okay. So we have n samples and d features. So you just add ones here, okay. So now you have n on over d plus 1, and then you can have a weight vector that includes the bias. Sorry? Where? Here? Yeah, I can try, but then you won't see the bottom part, so it's a bit too long. But okay, let's focus on that for a second. So what I did here is basically just add this column. Okay. Now I will use my weights to calculate the class probability of each of these samples, which is this function predicts proba. So this name is a standard name in sklearn, so I didn't invent it. But you can see, just ignore the add bias thing. What all it does is just do a multiply of the data with the bias times the weight vector. So I have a weight vector. This is my weight vector. It has d plus 1 over 1. Okay, so I'm just doing that. And then I get a prediction for each, at least a score. The z is a score, and then I use the logistic function to convert it to probability. Okay, so since I have a data matrix with samples in its rows, if I do that, I just use one matrix multiply to get my z. Z is also a matrix, and then it's a column. And then I use the logistic function to get the probability of each sample. That's what you see here. It's really, really simple. So that was this part, okay? And the next part is where actually we train the model. So the first thing we need to do is, after we have our predicted probabilities, y hat, we have to calculate the loss. Okay, so we're going to use the cross-entropy loss that I explained before. Simply apply the formula for the cross-entropy loss using our predicted values y hat. So when we had z, then we did sigma of z, and we called that y hat. Okay, so we're calculating the loss using that. And then we're gonna calculate the loss gradient. So this term is just taking the derivative. You can either do it in matrix form or use the pointwise loss and calculate. But basically, what you do is you calculate the L to dW. Okay, so it's a nice exercise in linear algebra, and you'll get a very, very simple result if you do it. You have to remember the derivative of the sigmoid function and try to get it. So I wrote down below that I left it as an exercise how to get this expression. But this is really the kind of the traditional way to do the gradient-based approaches. If you want to do the approach, you have to calculate the gradient somehow. So in this case, I calculated by hand and just coded it into the model. So you can see it kind of depends on the features and the difference between the probability and the label. Okay, so after we have our gradient, we do a step, which is a gradient step, which we just take our gradient and update our weights using some kind of small number as our learning rate. So we're just taking the direction of the gradient with respect to our weights and updating our weights in the negative direction of the gradient. Okay, so it's just if our weights were here, we're going there. Okay, so you'll see much more about this algorithm. This is a very simple version of gradient descent algorithm. You'll see much more about it in lecture. This is just to kind of show you a working implementation and see some code. So I'm not really going into that. And like I said, it's a good idea to try to implement this derivation yourself. In the homework, you will do it yourself with a different loss function and a different model. So if you don't do it with that, you'll do it in the homework for some other thing. But you will do it by hand because it's really good practice to understand how to do that and do some matrix calculus and stuff like that. Okay, so that was our model. And the predict function is the last part. But all it does is really just take our data, predict the probability, the class probability of each sample, and then if the probability is greater than 5, we say that it belongs to the first class. So it's really not doing anything smart. So that's the whole model. Okay, that's the whole model. Okay, and here I'm just calling the fit function on my training data after I scaled it. And I'm showing you just a graph of the loss. You can see how the loss goes down. I'm training here for 1,000 iterations. You can see really the kind of loss graph. And it gets to a very low loss and kind of plateauing after 1,000 iterations. Okay, so let's use our test data to predict. So all we did here is after we trained our model with the fit function, we called the predict function on the test set to get the test predictions, and then we compared them to the test labels. Okay, and we calculated the percentage of correct predictions. So you can see on this toy data set, using a very, very simple implementation of a model, we get pretty good results. So don't expect that good a level of results that good in any kind of real problem, but at least not that easily. But in this case, it was really easy. Okay. So some notes here. Yeah, so like I said, it's not really a good idea to run for a fixed number of iterations over the entire data set. And usually you also can't really hold your entire data set in memory like I did here. Just put everything in a single matrix and train over my whole data set each time. So these things won't really work. We'll see in the following parts of the course kind of other ways to deal with that when we work with batches of data. You also see that in the first homework. And as I said, the actual core part of the model, the most important part of the model was the line with the gradient. So I left that kind of as an exercise, how to derive it. It's kind of long, but it's really simple. So you have to just do the calculus and you get there. And like I said, you'll see kind of a very simple, similar thing in the assignment. Okay, so let's move on to the multi-class problem. So now we'll kind of do a similar thing. A slightly more complex model, but this time we'll use PyTorch, and we won't derive the gradient ourselves. So in our multi-class logistic regression case, we don't have two classes. We have C classes, and we want to know if we can still use logistic regression. So I don't know if you have an idea, but a really simple approach would be just to take each class and train it against the other classes. This is known as a one versus rest scheme. You can also train a bunch of classifiers of each class versus each other class, and you can combine these classifiers to create a model. So if you have only binary classifiers, that's what you can do to create a more complex model. But the problem is that we would prefer if we have, for example, if we would get per sample a probability distribution. So we would like a vector of C entries. Okay, so it has C entries, and each entry is the probability of that class. So for example, this last entry here would be the probability of the class C. So let's try to build a model that will give us that. For each sample, the probability that it belongs to which class. And then we can just take the class with the maximal probability. Okay, so let's define a function called Softmax, which again, you will see it a lot. It's defined as follows. For it's vector valued, meaning it returns a vector, and its argument is also a vector. So here we have a vector z. We take the element-wise exponent of z, and we divide it by the sum of exponents of the elements of z. Okay, so it's vector valued. Vector valued returns a vector because this is a vector, and we just divide by a scalar. And what we get is a vector that of elements that sum to 1, and each element is 0 to 1, which means we can interpret it as a probability distribution over C classes, just like I said that we would like to have. Okay, so all we're going to do with our model is use the same affine transform as our starting point to transform our features, but then we're going to apply softmax on that. And this time our weights won't be a weight vector, but a weight matrix. Okay, why a matrix? Because effectively we have d weights for each class. So basically we're taking our sample, using a matrix that for each class calculates a score, and then we're taking that score and applying the softmax function to get a probability distribution over all of the classes. Okay, so again we have an interpretation as follows. Given a sample x, the probability that it belongs to class J is the jth element of our vector. Okay, so before the y hat was a number 0 or 1, now it's a C element vector. Okay, so that's how we extend the model to the multi-class case. So it's pretty straightforward now. We would also like our labels to be probability distributions. So what we're going to do is create what's called a one-hot representation, or one-hot encoded vector, which kind of corresponds to a singleton distribution. So if our sample for label I, for sample I, our label for sample I is class J, then we'll just create a vector with the jth component to 1 and the rest to 0. So we want our model to create these singleton distributions. Effectively, it will create a distribution of some other probabilities, but we want them to get to that. So we're training with these labels instead of the original labels. Okay, and the cross-entropy loss in our multi-class case will be this loss. So here this is our one-hot encoded vector. So remember, it's a vector, only one element is 1, the rest are zeros. So it's effectively selecting the element from this vector that has the correct class and using that predicted probability. Okay? Is that clear? Okay. So again, we're trying to create something that looks like the delta distribution using our predicted distributions. Okay. So let's tackle a different problem. We'll use a very popular data set called MNIST. It's a data set of handwritten digits. It's just images, black and white images of digits. And it's kind of used as a very simple benchmark for various machine learning algorithms. It's a completely solved problem with deep learning today. But we'll apply our simple multi-class logistic regression model to this task. Okay, so this time, instead of using NumPy and sklearn, we're going to do it with PyTorch just to see some basic concepts of PyTorch, which you will explore much further in the homework, and the rest of the tutorials will just use them. Okay, so what I'm doing here, let's run this. Okay, so let's start from the end. So this is an example of our data. You can see a bunch of images here of written digits that I got from the MNIST data set. What I'm doing here is I'm using PyTorch that has it has a module called Torch Vision, which also provides a bunch of data sets. This time they're much larger data sets, so it has to download them. In this case, I already pre-downloaded them. Okay, so I'm using these data set objects that you will see later what they do, but they just kind of give you a way to wrap your data and load batches from it. Okay, so that's why I'm specifying a batch size, which means I'm loading 128 images each time from my data set on disk. So in my memory, in my RAM, I'm just keeping 128 images. So that's kind of how I'm loading my data in this case. And I'm just taking the first element of my training data set, which is a tuple containing an image, or at least a batch, and the labels. Okay. So this is the first image. And sorry, here I'm printing the first 10 images from my data set. So that's why you can see 10 images here. Okay, so this is just kind of boilerplate code to work with data sets in PyTorch. Let's continue. So let's build our model now. Okay, another thing I want to mention here is that we're not going to calculate the gradient by hand this time. We're going to use a part of PyTorch called AutoGrad, which is a very important functionality. It's actually crucial when you do deep models where you don't want to calculate the gradient of the loss by hand, because the loss is a function of many layers of nonlinear functions. So it's kind of much harder to compute your gradients. So a very important feature of many deep learning frameworks, not just PyTorch, is the fact that it calculates the gradients for you. So you just do some operations on a bunch of tensors, and you can say, I want gradients for that from a specific loss. So this relates to something called backpropagation, which again you'll see in the lecture, and you'll also implement it in homework too. But I'm just showing it now kind of as something that you can use, and you don't have to really dive into that. Okay, so let's start with our model implementation. So the first part that we're going to need is the Softmax function, as I defined it before. So these two lines are just a trick to make the implementation more stable. It shifts all the elements of the vector z to have a maximal value of 0. And then these two lines are really just very like you saw in the formula. You just take the element-wise exponent of z and divide it by the sum of elements. Okay. So again, there are some broadcasting issues that you need to consider here. For example, the reason keep dim is true here is because of broadcasting considerations. So when you implement it, you need to kind of think about what shapes you're getting and how to use those shapes to create an efficient implementation. So for example, here I want to divide each element by the same number. So I want to use broadcasting, but I have to kind of think about my shapes to do that. Okay. So the next part is our cross-entropy, which we saw is very simple in this case. We take our one-hot representation and just multiply it. This is an element-wise multiplication by our predicted probabilities. Oh, another thing to note about this implementation is that it works with batches of data. So that's why our shapes here are n rows and c columns. So we have a batch of n samples that we're working with directly each iteration. Okay, so this is, again, something that you'll do throughout all your model training. So I'm just showing it here. And the last kind of building block that we're gonna define is an optimizer. So this is similar to the line in our previous model where I said there's a gradient step that we manually calculated the gradients. But here we're just kind of using some kind of magic. At least for now, it's magic. But you'll see it's very at least well defined, and you will implement it yourself, so you will understand how it works. So we're just using a built-in feature here that will give us the gradients of the parameters that we're optimizing. So just magically, instead of calculating it by hand, we just have the gradients here. Then we're using the same gradient descent formula to just update our parameters based on their gradients and a small number called the learning rate. Okay. Great. So this is this function. Okay, so we need to convert our labels to one-hot vectors. So that's what it does here. So I'm not going to go into that. It's just some vector functions that I used. Okay, and now the model itself. After we have all our building blocks defined, the implementation is really simple. I just want to showcase a few things here. So first of all, our parameters of the model parameters here. So we have a matrix W. We initialize it to random numbers, n by c, okay, not features by classes. And we specify this kind of optional argument, which means requires grad equals true. It means that when we do some operations on these tensors, they are recorded. There's a graph that's built of operations. Again, you will learn about it in the lecture about backpropagation. And this allows us to calculate the gradient of the loss. The forward part of the model, which calculates the probability, the class probability of each sample, is really straightforward. It's just a matrix multiply of our data with our weights, adding the bias term. This is a bias vector now. Okay, and doing the softmax of that, of the scores, so you get the class probabilities. So again, once we have all the building blocks in place, the implementation is actually very trivial. To evaluate our model, we will define this function to evaluate accuracy. So it showcases another important thing, which is how to go over our data. So what we're doing here is we're taking our data loader, which is one of the objects that we saw before when we used the PyTorch data sets. So this is an object that returns batches of data from our data set. It wraps the data set. So here we loop over it, so we get tuples of data. So this is a tensor of images, and this is their label. And this is just the iteration index. So we flatten our images first, because this model just treats every single pixel in the image as a separate feature. That's all we're doing here. Okay, and we're forwarding our data through the model to get our y-hat predictions. This line here means that we don't want gradients to be calculated. Even though we specified that some tensors here in the model should track gradients, just when we evaluate the model, we're not training it now, we're just evaluating, so we don't want to waste time on recording the computation graph that's created by the forward of the model. Okay? So after we get our predictions, we can take the maximal prediction to get our class label and compare it to the actual class label that we got from our data set. That's how we get the number of correct predictions for this batch. So then all we do, we sum it and calculate the accuracy. So here you can see I can just run it a few times. You can see accuracies of around 10%, okay, which kind of makes sense since we have 10 classes and the model was initialized with random weights. So since we have 10 classes, we can assume the model is just doing a random guess right now. It's not trained at all. Okay. So now let's train it. I'll just run it because it takes a few minutes. So let's go over the training code. Again, I'm showing you this because this is really similar to a lot of training code that you're going to write. Even if, like I said, I'm not going into all the specifics because you'll just see them later. But this whole kind of training loop is kind of a recurring theme. So let's understand it. So first of all, we create our model here. We have some hyperparameters that define how we're going to train, for example, the learning rate. We define an epoch, which is defined as one iteration over all your data set, your whole data set. So that's an epoch. So for example, in this case, we set the number of epochs to 3. We're just going to go over our data 3 times. This data set is about 60,000 images, I think, by the way. So it's pretty big. And that's why I'm only going over it 3 times in this tutorial. So for each epoch that we're going to do, we're going to go over our training data set. So this is our data loader. Again, remember, the data loader is a wrapper around the data set that returns batches. So here I'm getting a batch of 128 images each time. Okay, I'm flattening each image just into a feature vector, and I'm encoding my labels to a one-hot vector with my function that I implemented before. That's what's going on here. So after I have my reshaped data and my one-hot encoded labels, I forward my data through my model, which gives me the probability of each class for each sample after the softmax. And then I can pass it through my loss function, the cross-entropy that I implemented before, again using the one-hot encoded real labels and the predicted labels. This is my loss. Okay, so now the kind of autograd magic happens. After I have a loss, this loss is based on a bunch of calculations. So the first calculation was the matrix multiply. Okay, so I took my data and multiplied by the weights. And then I did a cross-entropy loss. So there was a log there and a bunch of other calculations. And then a softmax exponentiation. So there are a bunch of calculations there. And basically, finally I got a loss, a number. Okay, I got a number. And I want to compute the loss with respect to my weight matrix in this case. So if my loss is a scalar and my weight this is a matrix, then this derivative should be also a matrix with the same dimensions as the weight matrix W. Okay, this backward call is what goes over the computation graph that was created when we computed the output of our model. And it stores in each tensor that we requested requires grad equals true, it stores the gradient. Okay? And again, the gradient of what? The gradient of the loss with respect to that tensor. So we had W and B. So our W will have the loss, the gradient of the loss with respect to it, and we will also have the gradient of the loss with respect to our B vector. So this is a matrix, this derivative is a matrix, and this is a vector. Okay, so just explaining it high level now, and we'll dive into this in the future. After I have a loss, I'm using my SGD optimizer function, which, as you recall, it uses the grad property of each tensor to update. So I'm giving it the parameter tensor. So this params is basically just a list of my W and B, okay? And it's going over them each one, and it's saying, it's taking the W.grad, okay? And it's using that to do the gradient descent step. And we know this exists because of the loss backward call here. Okay, so again, this is a kind of recurring theme when you use PyTorch. This is kind of the same training loop that you will write regardless of the model. At least these rows kind of look the same all the time. Okay, so after we have a loss, we updated our parameters. We'll also keep a cumulative sum of the loss. And you can see down here that I already ran my 3 epochs. So first epoch, we got a pretty high loss. Our test accuracy, which is really what we care about, was 83%. Which, as you can see, after 3 epochs, we got about 90% accuracy on this MNIST dataset. So again, a very simple toy dataset, but this was much more data. So this was about 60,000 images, and a very simple model which we implemented with very few lines of code, and we got pretty good results. Okay. Oh, sorry, I didn't mean to run it again. All right. So just kind of keep in mind, this implementation was kind of naive. Okay. And it wouldn't really, don't count on it for really more complex problems. Even though we got pretty good results. The other point here is that much of the things that I implemented here by hand, you get kind of built in PyTorch. We could have used these things, but I try to kind of do as much from scratch as I can. But also, I wanted to show the autograd functionality, so I kept that in because it will kind of help you understand what's going on later. And the last thing is that you can, if you want, you can try to implement, instead of using the autograd feature and using the grad of each vector, just kind of do the loss calculation by hand and replace that line of code, and you should get a model that still works. And it's also it's not hard to do this derivation by hand, at least for the logistic regression, even in the multi-class case. It's kind of it's a bit long, but like I said, it's doable. Okay. So I think that's it, unless you have any questions. Okay. Thanks.